In today's video lecture, we are going to finish the packet of notes dealing with sinusoidal steady-state analysis. The first topic we're going to look at is handling inputs of multiple frequencies. What do I mean by this? Suppose you have a circuit where either your voltage or current sources have input signals that have more than one frequency present in them. This is going to cause a problem for two reasons. First off, the whole phasor concept itself assumes that you're operating at a single frequency, and that's not going to be the case here. Secondly, when you convert the capacitors and the inductors to their equivalent impedances, the frequency term omega shows up in the impedance. It's either negative j over omega c or positive j omega L. So what happens if you have more than one frequency present in the signal? Which omega do you use? So that is the second problem. So we're going to see that whenever you have a circuit where your inputs consist of more than one frequency, you're going to have to use superposition. So here's the algorithm. The first thing you need to do is pick one of the operating frequencies in your circuit. So the first thing you would do is deactivate all inputs that are not of that frequency. By that, I mean that if you have a voltage source, replace it by a short circuit. And if you have a current source of another frequency, replace it by an open circuit. The second thing you would do is for the frequency you've selected, determine the corresponding impedance of every capacitor and inductor in that circuit. Then you solve the circuit using any of the sinusoidal steady-state analysis techniques we've talked about over the past couple lectures. We convert the output phasor back to the time domain using that frequency of operation. And then what we do is we go back and do the same four steps for every other frequency present in the circuit. At the very end, what we want to do is combine the final time domain expressions into your final answer. The key thing here is you cannot add your voltages and currents in the phasor domain. You have to do it in the time domain because the different phasors each correspond to a different frequency. So let's do a couple examples to illustrate this idea. So here we have a fairly simple circuit, one capacitor, one resistor, and one voltage source, but the voltage source itself consists of different frequencies. We have a DC component where omega is 0. We have another component where omega is 25 radians per second. And then we have two other frequency components where the frequency is 1,000 radian per second. So the idea here is to break this circuit into three subcircuits, one with omega of 0, one with omega of 25, and one with omega of 1,000. Before we do that, it's probably easiest to get a general expression relating VC phasor to VS phasor so we can just plug values in at the end. So in the phasor domain, circuit looks like this. We have a voltage source VS phasor. The resistance, 20 ohms, is frequency independent. The impedance of the capacitor is minus j over omega c. C is 2 millifarads, so we get minus j over 0.002 omega ohms. And of course, the voltage across that is VC phasor. And from voltage division, VC phasor is just minus j over 0.002 omega over 20 minus j over 0.002 omega times Vs tilde, multiplying the numerator and denominator each by 0.002 omega. We then get minus j over 0.04 omega minus j times Vs tilde. Okay, so let's look at the different situations. The first situation is when the frequency is 0 radians per second. Vs1 tilde now is just 5 at an angle of 0 degrees volts. Vc1 tilde is going to be what? It's going to be minus j over 0.04 times 0 minus j times Vs1, which is minus j over minus j times 5 at an angle of 0 degrees, which is 5 at an angle of 0 degrees. So in the time domain, it's 5 cosine of 0t, or 5 volts. Now let's set our frequency to 25 radians per second. Vs2 tilde is now going to be what? It's going to be 5 sine 25t plus 45 degrees. Because it is a sine, we have to subtract 90 degrees from the angle, but then you add 45. This now becomes 5 at an angle of minus 45 degrees volts. So Vc2 tilde is what? It's minus j over 0.04 times 25 minus j times 5 at an angle of minus 45 degrees. You work out the math there. It is 3.54 at an angle of minus 90 degrees volts. So that means in the time domain, this is 3.54 times the cosine of 25t minus 90 degrees volts. Now we go back and do it a third time with the frequency of 1,000 radians per second. Now in this case, we have two different components to the time domain input signal. So what is Vs sub 3 phasor? In this case, Vs3 phasor is going to be 3.536 at an angle of 0 degrees, that's the cosine term, minus 3.536, the sine term is just the cosine term at an angle of minus 90 degrees. And you work out this math, you actually get 5 at an angle of 45 degrees volts. In other words, what we're saying is 3.536 cosine of 1,000t minus 3.536 sine of 1,000t happens to equal 5 cosine of 1,000t plus 45 degrees. Anyway, continuing on, what we know is that Vc3 is going to be what? This expression here, it's minus j over 0.04 times 1,000 minus j. It's going to be minus j over 0.04 times 1,000 minus j times Vs sub 3. Minus j is 1 at an angle of minus 90 degrees. The denominator becomes 40.0125 at an angle of minus 1.43 degrees times 5 at an angle of 45 degrees. It becomes 0.125 at an angle of minus 43.57 degrees volts. So in the time domain, this is 0.125 cosine of 1,000t minus 43.57 degrees volts. So we can now put the answers together, but we're not adding this, this, and this together because those phasors each correspond to a different operating frequency. Instead, the terms we add together are the three time domain expressions. So Vc of t, when you put it all together, is going to be 5 plus 3.54 cosine 25t minus 90 degrees. That was the term down there. Plus 0.125 cosine of 1000t minus 43.57 degrees volts. And this is our final answer. One thing to look at. The input, we said before, is composed of 3 different frequencies. All 3 frequencies have the same amplitude. We had a DC of amplitude 5. We had a 25 radian per second signal with an amplitude of 5. And we had a 1000 radian per second signal, which we saw on this page, also had an amplitude of 5. So at the input end, all 3 frequency components had the same amplitude. But look at the output end. The DC component still had an amplitude of 5. The 25 radian per second component had an amplitude of 3.54, and the 1000 radian per second component had an amplitude of 0.125. In other words, we had no attenuation at DC. We had some attenuation at 25 radians per second, and we had lots of attenuation at 1000 radians per second. And this illustrates the frequency-dependent aspect of the circuit. This particular circuit is what we call a low-pass filter. By low-pass filter, we mean that it allows low frequencies to pass through. We will look at this topic in much more detail in the next packet of notes. But at this point, we just illustrated how we can use superposition to handle a circuit with inputs of multiple frequencies. So now let's look at a different example. This example is different than the first example because here we have 2 different sources, each one operating at a different frequency. In the previous example, there was only one source, but it had 3 different frequency components in it. Nevertheless, the process for solving this circuit is the same. We're still going to use superposition. So we're going to start by considering the circuit only at an operating frequency of 1000 radians per second. So in this case, the current source is activated, but the voltage source is not, because the voltage source is operating only at 2000 radians per second. So the current source becomes what? It becomes a phasor 2 at an angle of 30 degrees amps. The 3 ohm resistor is frequency independent. The 2 ohm resistor is frequency independent. The capacitor has an impedance of minus j over omega c. When omega is 1000 radians per second, this becomes minus j 2 ohms. The inductor has an impedance j omega L, so at 1000 radians per second, this becomes j1 ohm. And the voltage source, because of superposition, is now shorted out. It looks like that. And what we're looking for is the voltage across the 2 ohm resistor. We'll call that Vx sub 1 tilde. Well, turns out the Vx1 tilde is just 2 times the current through this branch here. We'll call that current Ix1 tilde. So Vx1 tilde is 2 times Ix1 tilde. But what is Ix1 tilde? Well, we can use current division for that. The total current going into the two branches on the right is 2 at an angle of 30 ohms. Some of it is going to go through this branch. Some of it is going to go through that branch. So from current division, Ix1 is equal to what? It is equal to the opposite impedance, which is J1, over the sum of the two impedances, 2 minus J2 plus J1 times the total current, which is 2 at an angle of 30 degrees amps. So that is the current Ix1. And then we have to multiply it by this 2 to get the voltage. You work out all this math, you get 1.789 at an angle of 146.6 degrees volts. So Vx1 in the time domain is 1.789 cosine 1000 t plus 146.6 degrees volts. Now, superposition, we'll consider the second frequency. Now, in this case, the current source is no longer present because the current source does not have any component at 2000 radians per second. And of course, a 0 amp current source is an open circuit. This leftmost resistor is frequency independent. This 2 ohm resistor is frequency independent. The capacitor now is minus J over omega C, but now omega is 2000 radians per second, so now we get minus J1 ohm. And notice that's different than what we had in the previous case. Likewise, the inductor is J omega L. Since omega is twice what it was before, its impedance is twice what it was. So once again, there's a difference in the two circuits in both the capacitor's impedance and the inductor's impedance. Now the voltage source does exist in this case, and its value is 8 at an angle of 45 degrees. And once again, we're looking for this voltage. We'll call it Vx2 tilde. So the first thing we see is this branch here on the left really has no effect, and we can just use voltage division. The voltage across the 2 ohm resistor is its impedance over the sum of these three impedances times this voltage source. So from voltage division, we get that Vx2 tilde is 2 over 2 minus J1 plus J2, all of that times 8 at an angle of 45 degrees. You work out the math, it becomes 7.1552 at an angle of 18.4 degrees volts. So Vx2 in the time domain is 7.1552 cosine of 2000 t plus 18.4 degrees volts. Finally then, we put these together, and once again, we're not adding this term and this term. Instead, we're adding this term and this term. So Vx of t is 1.789 cosine 1000 t plus 146.6 degrees plus 7.1552 cosine of 2000 t plus 18.4 degrees volts. So we see in these two examples, whether you have two different sources operating at two different frequencies, or a single source operating at multiple frequencies, you use the superposition principle and do a sinusoidal steady state solution for each frequency and then add the final time domain answers together. The last topic we're going to look at is covered in section 912 of the book. So you want to read section 912 of the book. And this is a concept called phasor diagrams. A phasor diagram is basically a visual tool to help us see the different voltage and current phasors present in a sinusoidal steady state circuit. And it's based upon putting vectors on a complex plane. Complex plane is a plane where the x-axis is the real axis and the y-axis is the imaginary axis. The whole idea behind a phasor diagram is it gives us a quick and dirty way to look at the relative voltage amplitudes, current amplitudes, and phases of the different voltages and currents present in the circuit. And because we are representing these voltage and current phasors as vectors, we can use vector arithmetic if we wanted to add things together. Let's illustrate this with a simple example here, and then we'll do another example on the next page. Suppose you have a resistor, capacitor, inductor all in series with some voltage source Vs, and this is unknown at this point. But suppose we know that the current has a phasor of 4 amps. So this is 4 at an angle of 0 degrees amps. We actually don't even know what the frequency of operation is here, but that doesn't matter. We know that the current magnitude is 4 at an angle of 0. What we can do then is we can put all of the various voltages and current phasors on this phasor diagram to the right. So for example, the current 4 at an angle of 0 is just 4 plus J0. So it becomes this vector right here, 4 plus J0. The voltage across the resistor we know is in phase with the current through the resistor, and its amplitude is going to be 2 times the current amplitude. So the voltage across the resistor, VR phasor, is now this vector here. Notice it is 8 plus J0. How about the voltage across the inductor? We know that for an inductor, the voltage leads the current by 90 degrees, and we know because the impedance is 0.75 J, we know that its amplitude is going to be 3/4 of the current amplitude. So if the current had an amplitude of 4, the voltage across the inductor is going to have an amplitude of 3, and it's going to lead it by 90 degrees. Here's our 90 degrees here. And so we see that the voltage across the inductor is 0 plus J3 volts. And we get that also by taking J times 0.75 and multiplying it by 4 at an angle of 0 degrees to get that. How about the capacitor? The capacitor, we know that the current leads the voltage by 90 degrees, and we know because this had an amplitude of 1.25 in the impedance that the voltage is going to be 1.25 times the amplitude of the current. So if the current had an amplitude of 4, the voltage is going to have an amplitude of 5, and it's going to be 90 degrees less than the current. So the voltage across the capacitor is 0 minus J5 volts. We could also get that by multiplying minus J 1.25, the impedance times the current. That's going to give us the voltage. Finally, what we see is that the voltage source has to equal the voltage across the resistor plus the voltage across the inductor plus the voltage across the capacitor. Doing KVL here. Minus Vs plus VR plus VL plus Vc is 0. And so we see that the source voltage is just the vector addition of the resistor the capacitor, and the inductor. If you remember how you add vectors, you add tails to heads. So if you have the resistor voltage, that's the blue vector, we add to that the red vector. Once again, you add tail to head. We add to that the green vector, that is the capacitor voltage. It's going to look like that. And we get that the source voltage is that vector here, which is 8 minus J2 volts, which in polar form is 8.25 at an angle of minus 14 degrees. So we see that the phasor diagram gives us a quick and dirty way of looking at the different voltages and currents present in the circuit. Let's do another example. So in this circuit, we're given a voltage source, we're given a resistor, and we're given an inductor. And we're told that the voltage across the voltage source is 10 cosine of 1000t, which means its phasor is 10 at an angle of 0 degrees volts. So what's the current? We know from Ohm's law that IL, which in the phasor domain is that, IL phasor is just Vs phasor divided by the impedance, which is 2 plus j omega L. So it's 10 at an angle of 0 degrees volts over 2 plus j. Omega is 1000 radians per second. L is 0.001 Henry. So 10 at an angle of 0 volts over 2 plus j1 ohms. We get 4 minus j2 amps. The voltage across the resistor in the phasor domain is that. We'll call it VR tilde. VR tilde is just 2 times IL tilde, which is going to be 2 times 4 minus J2, which is 8 minus J4 volts. VL tilde is just going to be J omega L times IL tilde, which is J1 times 4 minus J2, which is going to be 2 plus J4 volts. We can now put these all on the phasor diagram. Vs is 10 at an angle of 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is Vs. Our current, we'll put in red, it's 4 minus J2. That's our current. IL, which is also IR. We know the voltage across the resistor is in phase with the current through the resistor, but twice the amplitude. It's going to be 8 minus J4. Notice that VR and the current are in phase with each other. The inductor has a voltage that is 90 degrees leading the current, and its value is going to be 2 plus J4. So VL tilde looks like that, and notice there is a 90-degree angle here. The final thing we note is that Vs is equal to VR plus VL. Sure enough, if you add VL to VR, remembering adding tail to head, you get VR plus VL equals VS. So the bottom line here is this phasor diagram where we show one current, because it's a series circuit, one current and three different voltages, VL, VR, VS, are all shown nice and neatly in one diagram here, which makes it easy to see the relative amplitudes and phase angles of the different variables. The final thing we're going to look at is how these phasor diagrams relate to the final time domain waveform. So imagine your phasor diagram on your complex plane. So we have three different vectors here, one there, one there, one there. Let's start rotating this counterclockwise with the frequency of omega radians per second. Then what we'll do is we'll take the tip of each phasor and project it onto the x-axis, onto the real axis. For example, this one projects to there, this one projects to there, this one projects to there. What that means is that at that instant in time, that is what the value of that waveform is going to be. And as you rotate this vector counterclockwise, the x-axis projection is going to go back and forth along the plane here. If you use a reflecting line, then you can take a certain value, bring it down to here and across to here, and that gives you the corresponding time domain expression. This is best illustrated with a live animation. So here we have our three vectors, red, blue, and green, on our complex plane, and we see that we project it down over to this reflecting line and over. As we start rotating the vectors, what happens is we see that the head of the vector comes down and across, and we start tracing out our sinusoids. So let's go through a couple times here. You see what happens. So the rotating phasors in the time domain give us our sinusoids. And once again, at any instant in time, you see where the head of the vector goes to, bring it to the reflecting line and across here, and we see that's the value. And we can get to a point, for example, at this point here, the blue vector, its x-axis equivalent is 0. Sure enough, it is 0 on the x-axis. And go to another point where you get maximum amplitude for the blue. That's right around there. It's negative in this example. But once again, the x projection is all the way over, and so we get our maximum amplitude of 10. And so this is the physical relationship between the phasor diagram and the resulting time domain expression of the different voltages and currents in the circuit. So going back to this diagram here, you can hopefully understand where the blue, the green, and the red diagrams on the right come from. This concludes the packet of notes dealing with sinusoidal steady-state analysis. It does not conclude this topic by any stretch of the imagination. We are going to extend this whole topic into the next packet of notes dealing with frequency domain. Have a good day.